The universe appears chaotic, but a deep, hidden symmetry governs everything. This elegant order is the secret force holding reality together, like a perfectly balanced cosmic clock ticking with unseen principles. By the end of our journey, you will see the cosmos through a new lens, understanding how this symmetry unlocks the birth of the universe and the very nature of matter. What if the key to reality's greatest mysteries lies not in complexity, but in beautiful, simple patterns? How does a concept so abstract explain why anything exists at all? What does it feel like to glimpse the fundamental order behind everything we see? That intuition of a hidden cosmic order is not a modern discovery. It echoes across thousands of years, whispered by the first philosophers who dared to look up. Ancient Greek thinkers like Pythagoras listened to the music of the spheres, convinced the planets moved in perfect, harmonious ratios. They believed the universe itself was built from numbers, a grand symphony of mathematical relationships. This was not just philosophy. It was a deep, spiritual conviction that beauty and order were the fabric of reality. Centuries later, Johannes Kepler was so captivated by this idea he tried to fit the orbits of the planets around the 5 Platonic solids, those perfectly symmetrical three-dimensional shapes. He envisioned a cosmic clockwork of nested spheres and geometric forms, a physical model of divine harmony. Why were these brilliant minds so obsessed with perfect shapes and musical intervals? They were searching for the user manual of the cosmos, convinced that the creator, whatever form that took, was a master mathematician. They saw symmetry not as a pretty decoration, but as the foundational principle of existence. This ancient quest reveals something profound about our own place in the universe. We are pattern-seeking creatures, and our drive to find balance in the stars reflects a deep need to understand our home. The baton of this search has been passed down through the ages, from mystics to astronomers, and now to physicists with powerful particle colliders. The tools have changed, but the fundamental question remains the same. What is the ultimate pattern that holds it all together? This ancient obsession with cosmic harmony found its mathematical voice in the rise of classical physics. Think of a simple pendulum swinging back and forth with perfect, predictable rhythm. Its motion is symmetrical, not just in its path, but in the very laws that govern it. The physics of that swing are identical whether it happens now or an hour from now. This invariance under transformation, the idea that the laws of physics do not change with time, is a profound type of symmetry. It is the reason our universe is predictable and stable. Why does a spinning ice skater accelerate when she pulls her arms in? The answer lies in a beautiful and powerful idea from mathematician Emmy Noether. Her theorem is a cornerstone of modern physics, revealing an elegant, unbreakable connection. It states that for every continuous symmetry in nature, there is a corresponding quantity that is conserved. The symmetry of time translation, the fact that physical laws are the same today as yesterday, gives us the conservation of energy. The symmetry of spatial translation, the idea that physics works the same here as it does in a distant galaxy, gives us the conservation of linear momentum. These are not just abstract concepts. They are the hidden rules that allow engines to run and planets to maintain their orbits. They are the reason the universe is not a chaotic mess, but a system governed by reliable, symmetrical principles. This framework of predictable cause and effect, built on these foundational symmetries, is the stage upon which our daily lives play out. But what happens when we look beyond this familiar stage, into the bizarre quantum realm where certainty dissolves into probability? Yet this predictable stage of classical physics shatters when we venture into the quantum realm. Here, symmetry transforms into something far more bizarre and fundamental. An electron does not simply exist in one place or with one spin. It exists in a blur of all possible states at once, a perfect symmetry of potentiality. This is not a flaw, but a feature of reality at its smallest scales. It is only when we observe it that this symmetry is broken, forcing the electron to choose a single, definite state. This strange behavior is governed by quantum fields, and the symmetries of these fields are not suggestions. They are absolute dictators of how particles can interact with each other. One of the most crucial is gauge symmetry. This is the idea that the laws of physics must remain consistent even if we change our perspective in a specific way, like tweaking the definition of an electron's field at every point in space. This seemingly abstract requirement is the very reason the electromagnetic force exists and behaves as it does. It is a symmetry that enforces consistency, weaving the fabric of forces. The great physicist Richard Feynman saw these quantum symmetries not as mathematical curiosities, but as the essential tools for predicting how the universe works. They are used to classify every elementary particle into families, known as symmetry groups, much like arranging elements on a periodic table based on their properties. But perhaps the most stunning role of symmetry in the quantum world is when it breaks. The Higgs mechanism describes a field that permeates all of space. In its original high-energy state, this field is perfectly symmetrical. But as the universe cooled, this symmetry broke, like water freezing into ice crystals. And just as ice crystals give a lake a new structure, this broken symmetry gave mass to particles, allowing them to form the atoms that build our world. This leads us to a profound question about reality itself, famously illustrated by Schrödinger's cat. Is the cat in the box both alive and dead? A symmetrical superposition of states until we look. Quantum symmetry forces us to confront a universe where the line between what is real and what is merely possible is fundamentally blurred. We are left wondering if existence itself is a tapestry woven from countless potentialities, held in a delicate balance until the moment of observation collapses it into a single thread. This cosmic periodic table is known as the Standard Model, and its organizing principle is pure symmetry. Think of it as a vast, cosmic filing system for every fundamental ingredient in reality. Particles are not sorted by weight or size, but by their symmetrical properties, described by mathematical structures called groups, like SU3 and U1. These are not arbitrary labels. They are the strict rules governing how particles can transform and interact. A quark, for instance, carries a property called color charge, which has nothing to do with visual color. It is a type of charge governed by the SU3 symmetry group, and this symmetry demands that quarks must exist in triplets, forever bound together to form protons and neutrons. It is the mathematical rule that literally holds atomic nuclei together. Similarly, the U1 symmetry group describes the familiar force of electromagnetism, dictating how light and matter interact. The physicist Sheldon Glashow once reflected that they were essentially following the trail of mathematical beauty, using symmetry as their guide. This pursuit led to one of the greatest triumphs of theoretical physics, the Electroweak unification. It revealed that the electromagnetic force and the weak nuclear force, which seem utterly different in our everyday world, are actually two manifestations of a single, symmetrical force that existed in the searing heat of the early universe. This unification was not just a neat idea. It made a bold prediction: the existence of the W and Z bosons, particles that were later discovered exactly as foreseen in particle accelerators. These colossal machines are the ultimate symmetry detectors, smashing particles together to recreate the primordial conditions where these fundamental symmetries reign supreme. When they discovered the Higgs boson, they were witnessing the final piece of this puzzle, the particle that emerges from the broken symmetry of the Higgs field. It is the tangible evidence of a cosmic cooling process that gave mass to the universe. So when you look at your hand, you are not just looking at flesh and bone. You are looking at a magnificent structure built by symmetrical laws, an architecture of existence written in a hidden mathematical language that we are only just beginning to understand. But the Standard Model, for all its beauty, is not the final word. Many physicists believe it is merely a low-energy shadow of a far grander, more symmetrical reality. This leads us to a theory so ambitious it proposes a hidden twin for every particle in existence. Supersymmetry, often called SUSY, suggests that every known fermion, the building blocks of matter like electrons and quarks, has a superpartner boson, a force carrier. Conversely, every boson, like the photon, has a superpartner fermion. It is a cosmic mirror, reflecting matter and force into one another, creating a perfect, hidden symmetry that doubles the population of the particle zoo. Picture the universe as a coin. On one side you have matter, on the other, the forces that act upon it. Supersymmetry posits that these are truly two faces of the same fundamental entity. Why would nature require such an elaborate setup? One of the most compelling reasons is known as the hierarchy problem. The mass of the Higgs boson is extraordinarily fragile, and according to the plain Standard Model, quantum fluctuations should have driven its value to an astronomically high number, making our universe impossible. But supersymmetry provides an elegant fix. The superpartners of known particles would produce canceling fluctuations, naturally protecting the Higgs mass and keeping the scale of our reality stable. This is not just a mathematical trick. It is a potential rescue of our entire cosmic story. Furthermore, supersymmetry offers a perfect candidate for the universe's missing mass. The lightest supersymmetric particle, often called the neutralino, would be stable, electrically neutral, and barely interacting with normal matter. It fits the description of dark matter perfectly, a shadow particle that could form the invisible scaffolding of galaxies. Theorists like Michio Kaku have championed SUSY for its power to unify the fundamental forces at incredibly high energies, suggesting that in the first moments of the Big Bang, gravity, electromagnetism, and the nuclear forces were all one, described by a single supersymmetric framework. Yet for all its mathematical elegance, nature has so far been silent. The Large Hadron Collider, designed to probe these very energies, has not yet found any direct evidence for these superpartners. They were predicted to appear at energy scales we have already accessed. Their absence has forced a profound and ongoing debate within physics. Is supersymmetry simply manifested at energies higher than we can currently reach? Or is it a beautiful dream, a mathematical mirage that does not reflect the true nature of our cosmos? The search continues, pushing our machines and our minds to their limits. This quest forces us to confront a deeper question about the universe. Is reality built upon layers of symmetry we have not yet uncovered, each more profound than the last? Or have we reached the edge of what our current concepts can describe? The silence of the colliders regarding supersymmetry forces our gaze backward, to the very beginning of everything. In the first fleeting instance after the Big Bang, the universe existed in a state of perfect symmetry. All the forces we now see as separate, gravity, electromagnetism, and the nuclear forces, were fused into one single, unified interaction. There was no distinction between matter and force. It was a hot, dense, and featureless primordial soup, a blank canvas of pure potential. This perfect order could not last. As the newborn cosmos expanded and cooled, it underwent a series of dramatic phase transitions, much like steam condensing into water and water freezing into ice. With each transition, a fundamental symmetry broke. Alan Guth, the architect of cosmic inflation theory, described these breaks as the moments that carved our reality. The first break might have separated gravity from the other forces. A later one split the electroweak force into the electromagnetic and weak forces we recognize today. Each broken symmetry crystallized a new law of physics, giving the universe its specific character and structure. This breaking was not a flaw. It was the engine of creation. One of the most pivotal moments was cosmic inflation, a period of exponentially rapid expansion driven by a scalar field known as the inflaton. Think of this field as a cosmic reset button. It stretched the universe from a subatomic speck to a vast volume in a fraction of a second, smoothing out any initial wrinkles and irregularities. This process imprinted a profound uniformity on the cosmos, a large-scale symmetry we can still observe today. The evidence for this is etched into the oldest light in the universe, the cosmic microwave background. This afterglow of the Big Bang paints a picture of a remarkably smooth and homogeneous early universe. Yet, embedded within that smoothness are tiny fluctuations, minute variations in temperature and density. These are the cosmic seeds, the scars of quantum jitters stretched across the sky by inflation. Every galaxy, star, and planet we see today grew from those infinitesimal imperfections in an otherwise symmetrical background. So we are left with a profound cosmic narrative. Our asymmetric universe, rich with structure and diversity, is the product of a sequence of broken perfections. The very laws of physics themselves, the rules that allow for atoms and life, may not be fundamental, but merely the unique outcome of a specific series of symmetry breaks in our particular cosmic bubble. This raises a staggering possibility. Could different sequences of symmetry breaking have created universes with entirely different laws, where gravity is repulsive or atoms cannot form? We are the products of a specific cosmic cooling process, a frozen artifact of a symmetry that once was, living in the intricate and beautiful fragments it left behind. Einstein's revolution wove symmetry directly into the fabric of space and time. His theory of general relativity reveals that the cosmos obeys the same physical laws no matter how you choose to label it, a profound symmetry known as general covariance. Whether you describe the universe from a rocket ship or a rotating planet, the underlying equations remain consistent. This is not just a mathematical trick. It is a statement that the laws of physics are independent of our viewpoint, a democratic principle written into the heart of reality. To grasp this, picture spacetime not as a static stage, but as a dynamic, flexible sheet. The symmetrical principles governing this sheet ensure that a ball rolling in a straight line here follows the same fundamental rules as a comet hurtling through the void elsewhere. This elegant consistency dictates precisely how matter and energy tell spacetime how to curve, and how that curved spacetime tells matter how to move. At the core of this idea is the equivalence principle, a beautiful and powerful symmetry in its own right. It declares that inertial mass, an object's resistance to being pushed, is exactly equivalent to gravitational mass, which determines its weight in a gravitational field. This is why all objects, regardless of their composition, fall at the same rate in a vacuum. A feather and a hammer dropped together will hit the ground simultaneously, because the nature of their motion is dictated by the geometry of spacetime itself, not by a force tugging on them. This symmetry between acceleration and gravity is the conceptual engine that drives the entire theory. We see the dramatic consequences of this geometric view in the most extreme objects in the universe. A rotating Kerr black hole is a perfect example of symmetry in action. Its structure is defined by its spin, creating a region of spacetime that is perfectly symmetrical around its axis, dragging the very fabric of reality around with it. As predicted by experts like Kip Thorne, this warping of spacetime leads to incredible phenomena. Light bends around massive objects, an effect called gravitational lensing that lets us see multiple images of a single distant galaxy. Time itself stretches and slows in a powerful gravitational field, a reality that must be accounted for by the atomic clocks on GPS satellites. Their precise timing would drift without corrections for both the speed they travel and the weaker gravity they experience in orbit. Without these relativistic adjustments, your phone's navigation would fail within minutes. This is symmetry with practical consequences, governing technology here on Earth while simultaneously sculpting the grand architecture of the cosmos. From the gentle curvature that holds planets in their orbits to the violent ripples of gravitational waves sent across the universe by colliding black holes, symmetry is the invisible hand weaving spacetime into a single, coherent, and dynamic whole. A perfectly balanced pencil stands upright, a state of high energy and unstable symmetry. The slightest breath, the faintest vibration will send it toppling, and in that fall, it chooses a specific direction. This simple act breaks its symmetry, but in doing so, it finds a stable, lower energy state. This is precisely what happened to the universe in its first trillionth of a second. The cosmos was in a state analogous to that upright pencil. A hot, symmetrical state where the electromagnetic and weak forces were one unified electroweak force, and particles like electrons and quarks were massless, zipping around at the speed of light. Then, as the universe expanded and cooled, it crossed a critical threshold. The Higgs field, which had been in a symmetrical, high-energy state, underwent a dramatic phase transition. It toppled like the pencil, settling into a new, stable configuration that broke the electroweak symmetry. Physicists visualize this with an elegant analogy called the Mexican hat potential. Picture a sombrero with a high peak in the center and a circular trough running around the brim. The symmetrical, high-energy state is the unstable peak. The stable, lower-energy states are anywhere down in the trough. When the Higgs field settled into this trough, it chose a specific point, breaking the original rotational symmetry of the hat. This process is not just a mathematical curiosity. It is the mechanism that gave mass to the universe. As other fundamental particles move through this now condensed Higgs field, they interact with it. Some particles, like photons, slip through completely unaffected, remaining massless. Others, like the W and Z bosons that carry the weak nuclear force, and particles like electrons and quarks, interact strongly, acquiring mass and slowing down from light speed. This is the cosmic switch that allowed matter to clump together. Without it, there would be no atoms, no stars, no structures of any kind, just a formless soup of massless particles eternally racing through the void. The confirmation of this breathtaking idea came from the tunnels of CERN. For decades, the Higgs boson was the final missing piece of the Standard Model, a theoretical ghost. The Higgs boson is not the Higgs field itself, but a ripple in it, a tangible excitation that proves the field exists. Its discovery in 2012 by the ATLAS and CMS collaborations was a monumental triumph. They had found the particle that emerges from the broken symmetry, the smoking gun for a mechanism that shapes our reality. Peter Higgs, the theoretical physicist who gave his name to the boson, was famously overwhelmed. He described the discovery as the culmination of a lifetime's work, a moment that confirmed a beautiful mathematical insight about how the universe acquires its substance. This was not just about finding another particle. It was about validating our deepest understanding of how symmetry breaking carves the laws of physics from a formless beginning. We can see echoes of this creative breaking all around us. When a piece of iron is heated, its atomic magnets point in random directions, a symmetrical, disordered state. But as it cools below a specific temperature, the Curie point, these magnets spontaneously align, creating a unified magnetic field. The symmetry is broken, but a new property, magnetization, emerges. This is a phase transition, just like the one the Higgs field underwent. Symmetry breaking is not a destructive act, it is a generative one. It is the fundamental process that took a perfectly symmetrical but featureless early universe and endowed it with the diversity, the structure, and the rich complexity we see today. The very fact that we exist to ponder these mysteries is a direct consequence of a symmetry that broke in just the right way, at just the right time. freezing into the physical laws that make our cosmic home possible. Yet even this creative power of broken symmetry holds a deeper secret. For the universe to exist as we know it, a fundamental rule had to be bent, a perfect mirror had to crack. The cosmos we inhabit is composed almost entirely of matter, but according to our most symmetrical laws, the Big Bang should have created equal amounts of matter and antimatter. These two opposing substances would have instantly annihilated each other upon contact, leaving behind a sea of pure radiation and nothing more. So why is there something instead of nothing? The answer lies in a tiny, crucial flaw in nature's mirror, a phenomenon known as CP violation. CP stands for the combined operations of charge conjugation and parity. Charge conjugation means swapping every particle with its antiparticle, turning an electron into a positron. Parity is like looking at the universe in a mirror, reversing all spatial coordinates so left becomes right. For a long time, physicists believed that the laws of physics were perfectly symmetrical under this combined CP transformation. A reaction involving particles should look identical to the mirror image reaction involving antiparticles. It was an elegant and seemingly unbreakable rule. But in 1964, James Cronin and Val Fitch made a shocking discovery. They were studying the decay of neutral kaons, exotic particles that can turn into their own antiparticles. They found that the rate at which a kaon decayed into certain products was not exactly the same as the rate for its antimatter counterpart. The mirror world was not a perfect reflection. It was ever so slightly distorted. Cronin later described the profound implication that this tiny asymmetry, this one part in 1,000 discrepancy, might be the very reason any matter survived the universe's violent birth. This CP violation is the cosmic loophole that allowed one extra matter particle to survive for every billion matter-antimatter annihilations. That minuscule surplus is everything we see today, every star, every planet, every one of us. Modern experiments continue to hunt for the source of this broken mirror. Detectors like Bell in Japan and LCB at the Large Hadron Collider meticulously study the decays of beauty quarks and other particles, searching for the precise mechanisms that favor matter over antimatter. They have observed CP violation in several systems, confirming it as a genuine feature of nature's weak nuclear force. But the amount we have found so far is not nearly enough to account for the overwhelming dominance of matter in our universe. This means there must be other, as yet undiscovered, sources of symmetry breaking. Perhaps new particles or new forces that violate CP in more dramatic ways. This search is one of the most urgent in all of physics, because it is fundamentally the search for our own origins. We are the children of an imperfection, the living evidence of a broken symmetry. Without this cosmic favoritism for matter, the universe would be a dark, empty void. So while we marvel at the perfect symmetries that provide the framework for reality, we must also celebrate the exceptions, the tiny flaws that made all the difference. The universe is not a sterile, perfectly balanced equation. It is a story, and every good story needs a twist. This radical idea that we are projections from a lower dimensional reality is known as the Holographic Principle. It proposes that our seemingly solid, three-dimensional universe with all its stars, planets, and people might be a magnificent illusion, a holographic movie projected from a vast, two-dimensional surface at the edge of space. Every event that happens here, in the volume of our cosmos, is perfectly mirrored by information encoded on that distant boundary. This is not a vague analogy, but a precise, mathematical symmetry that could finally unite the warring worlds of quantum mechanics and gravity. The seeds for this mind-bending concept were planted in the study of black holes. Physicists like Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, a measure of its hidden information, is not proportional to its volume, but to the surface area of its event horizon. Think about that for a moment. The amount of information a black hole can contain depends on the area of its surface, not the space inside it. This was the first hint that the physics of a volume might be described by a theory living on its boundary. Leonard Susskind and Gerard T. Hooft took this clue and ran with it, arguing that this was not just a quirk of black holes, but a fundamental principle of the universe. They envisioned a cosmos where the true, fundamental degrees of freedom, the ultimate bits of reality, live on a vast, shimmering shell at the edge of space. Our rich, three-dimensional experience is a grand projection from that flat screen. This holographic symmetry finds its most concrete form in a discovery from string theory called the AD-SCFT correspondence. This is a precise mathematical dictionary that relates a theory of gravity operating in a hypothetical higher dimensional space, known as anti-de Sitter space, to a conformal field theory, a type of quantum theory without gravity that lives on its lower dimensional boundary. They are two completely different descriptions of the same physical reality. A complex gravitational event, like a star collapsing into a black hole, can be perfectly translated into a complicated but gravity-free dance of quantum particles on the boundary. This is the ultimate expression of symmetry, a duality that says two seemingly unrelated worlds are in fact one and the same. To grasp the implications, picture yourself falling toward a black hole. From your perspective, you cross the event horizon and continue inward, unaware of any drama. But from the perspective of an observer watching from the safety of the holographic boundary, a very different story unfolds. They would see your image smeared and frozen just at the horizon, your information perfectly encoded on that two-dimensional surface as you appear to hover there forever. The holographic principle resolves the infamous black hole information paradox by stating that no information is ever truly lost inside the black hole, because a complete copy of it remains painted on the surface. So where does this leave us? It forces a profound shift in how we view reality. The deepest symmetries of the universe may not be hidden within the space we inhabit, but may instead be written on its outermost walls. The three-dimensional world we touch and see could be an emergent property, a secondary effect of a more fundamental, flat reality. This hints at a truly unified description of all physics, where the illusion of separation between quantum particles and the curvature of spacetime finally dissolves. We are left to wonder if we are living inside the most complex hologram imaginable, a cosmic projection whose source code is written in a language of perfect symmetry on the edge of everything we know. Our universe is held together by an invisible scaffold. This dark matter, which vastly outweighs all the stars and planets we can see, reveals its presence only through gravity. When astronomer Vera Rubin meticulously mapped the rotation of galaxies, she found something astonishing. The stars at the outer edges were moving just as fast as those near the center, defying the laws of gravity as we knew them. The only explanation was a massive, unseen halo of matter, a symmetrical, spherical cloud enveloping each galaxy and holding its stars in a gravitational embrace. This discovery pointed to a cosmos dominated by something we cannot see, a hidden architecture governed by its own symmetrical rules. What could this mysterious substance be? Many physicists look to symmetries beyond the standard model for answers. Supersymmetry, for instance, provides a perfect candidate, the neutralino. This hypothetical particle would be stable, neutral, and barely interact with normal matter, exactly matching the profile of dark matter. It would form vast, symmetrical halos around galaxies, its gravitational pull the only trace of its existence. Another elegant idea involves a particle called the action, born from a proposed symmetry designed to solve a different puzzle in quantum physics. These actions would be incredibly light and abundant, flowing through the universe in a wave like sea, their collective gravity sculpting the cosmos on the grandest scales. The evidence for this dark scaffold is etched into the sky. When massive galaxy clusters collide, as seen in the famous Bullet cluster, the event tells a dramatic story. Telescopes observe the hot, glowing gas of normal matter, slowed by its own friction, sitting between the two clusters. But by mapping the gravity through the bending of light, we can see that most of the mass, the dark matter, has sailed right through the collision, unaffected. It behaves like a ghostly, symmetrical substance that barely notices the normal matter it permeates. Meanwhile, an even more mysterious force is at work on the largest canvas of all. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. One of the simplest explanations is a cosmological constant, an energy inherent to the vacuum of space itself. This concept possesses a profound and simple symmetry, the idea that empty space has a constant, uniform energy density that does not dilute as the universe expands. This symmetry drives the accelerating push, stretching the cosmic fabric faster and faster over time. Observations from the Hubble Space Telescope, by measuring the distances to exploding stars in far-off galaxies, have confirmed this relentless acceleration. The interplay between these two dark components is what sculpts the universe we observe. Dark matter's gravity pulls matter together, seeding the formation of galaxies and vast, web-like filaments. Dark energy's repulsive push acts against this, determining the ultimate fate of cosmic structure. Together, they have imprinted a symmetrical pattern on the large-scale distribution of galaxies, a cosmic web of clusters and voids that mirrors the subtle fluctuations in the primordial universe. Solving the twin mysteries of dark matter and dark energy may be the greatest challenge in modern cosmology. It forces us to ask a fundamental question. Are we on the verge of discovering entirely new classes of symmetry, principles that govern 95% of the universe that remains hidden from our view? The answers will not only reveal what the cosmos is made of, but may ultimately rewrite our understanding of space, time, and the very laws of physics. But if the holographic principle suggests our reality is a projection, what is the source of that projection? String theory offers one of the most profound answers, proposing that the fundamental ingredients of the universe are not point-like particles, but unimaginably tiny, vibrating strings. Their different vibrational modes, like the notes on a guitar string, give rise to every particle we observe. An electron is one vibrational pattern, a quark is another, and the photon is yet another. This elegant idea naturally demands a far richer stage for its symphony. To be mathematically consistent, these strings must vibrate in a universe with not just 3 spatial dimensions, but 10 or even 11. The extra dimensions, the theory suggests, are curled up into shapes of incredible complexity known as Calabi-Yau manifolds. Picture these as the intricate, multidimensional body of a cosmic violin. The exact shape of this hidden geometry determines the resonant frequencies of the strings, which in turn dictates the symmetries and laws of physics in our observable 4-dimensional world. The specific pattern of particles, the strengths of the forces, even the existence of 3 generations of matter, could all be consequences of the precise way these extra dimensions are folded. This is where symmetry reaches its zenith. The mathematical structure of string theory is so deeply symmetrical that it naturally incorporates gravity and the gauge symmetries of the Standard Model into a single, coherent framework. For the first time, gravity is not a troublesome add-on but an intrinsic part of the vibrational spectrum. The graviton, the hypothetical particle that carries the gravitational force, emerges as a specific vibrational mode of a closed string. Pioneers like Edward Witten have explored the breathtaking mathematical elegance of this framework, known as M-theory, which suggests that the 5 different versions of string theory are themselves just different facets of a single, underlying, and more symmetrical reality. These are known as dualities. 2 seemingly different string theories operating in different realms can be physically identical, related by a symmetry transformation. It is as if a concerto and a heavy metal song were, at their most fundamental level, the same piece of music, just written in a different key. Another startling implication involves the concept of brane worlds. Our entire four-dimensional universe could be a vast membrane, or brane, floating within a higher dimensional space. The particles and forces we know could be stuck to this brane, like dust on a soap film, while gravity, as the geometry of spacetime itself, can leak into the extra dimensions. This could explain why gravity is so weak compared to the other forces, its strength diluted as it spreads through dimensions we cannot perceive. How can we possibly visualize such abstract concepts? Think of a painting. From a distance, you see a beautiful, coherent image in two dimensions. But as you move closer, you see the individual brush strokes that give the image its texture and depth. In string theory, our four-dimensional reality is that finished painting, while the vibrating strings and curled-up dimensions are the individual brush strokes, the underlying texture that creates the whole. This theoretical frontier expands our notion of symmetry to its absolute limit. Could the ultimate, unified law of the universe be written in a language of 10-dimensional vibrations? A cosmic music so perfect that it generates the illusion of space, time, and matter. We are left to wonder if the deepest truths of reality are not just hidden in plain sight, but are woven into the very fabric of dimensions we have not yet learned to see. This fine-tuning of the universe leads us to a deeply philosophical question. Why do the fundamental symmetries and constants have the exact values that allow for our existence? This is the core of the Anthropic Principle, an idea articulated by physicist Brandon Carter. It suggests the universe must be compatible with the conscious life that observes it. We are not passive bystanders in a random cosmos, but active participants whose very presence requires a specific set of rules. The cosmological constant is a stunning example. This value, representing the energy density of empty space, is astonishingly small. If it were just slightly larger, the universe would have expanded so rapidly that galaxies and stars could never have formed. A slightly different value would have resulted in a cosmic emptiness, devoid of any structure or life. The precision required is beyond comprehension, like balancing a pencil on its tip for billions of years. How do we explain such improbable perfection? One compelling answer lies in the concept of a multiverse. Picture a vast cosmic landscape, an infinite froth of bubbling universes, each born with a different set of symmetries and physical constants. In most of these universes, the symmetries break in ways that are sterile. Perhaps the electromagnetic force is too weak to bind atoms, or the Higgs field gives mass in a way that prevents chemistry. In those cosmos, no one is around to ask why. We find ourselves in one of the rare universes where the symmetrical properties, from the strength of forces to the masses of particles, aligned in just the right sequence to forge galaxies, planets, and ultimately, observers. Our existence, then, becomes a form of cosmic selection bias. We are not seeing a universe designed for life, but life that has emerged in a universe capable of supporting it. The profound symmetries we have explored, from gauge invariance to the conservation laws, might not be fundamental truths etched into reality, but rather the local bylaws of our particular cosmic neighborhood. They are the frozen accidents of our universe's specific cooling process. This perspective does not diminish the majesty of symmetry, it deepens the mystery. It connects the grandest cosmic principles to the most intimate fact of our own awareness. The universe is not just a place where symmetry exists. It is a place where symmetry had to exist in a very specific way for us to be here to notice it. We are the universe becoming conscious of itself, and the hidden symmetries we uncover are the very reason that consciousness is possible at all. The same mathematical elegance that governs spinning black holes and quantum fields is written into the very blueprint of life. Look at your own hands, two mirrored instruments of incredible dexterity. This bilateral symmetry, a body plan split into left and right halves, is a fundamental theme in the animal kingdom. It is not a random accident. For a creature moving forward through its environment, a symmetrical body allows for balanced, efficient motion, whether it is a fish swimming, a bird flying, or a human walking. But the influence of symmetry runs far deeper than mere body shape. The very molecule of life, DNA, forms a beautiful double helix, a spiral staircase where each strand is a perfect mirror of the other. This structural symmetry is the key to reliable reproduction, allowing the two strands to unwind and serve as templates for new copies. This is not just about aesthetics, it is about optimal function. A sunflower's face is a masterpiece of radial symmetry, with seeds arranged in intersecting spirals that follow the Fibonacci sequence, a mathematical pattern that packs the maximum number of seeds into the smallest possible space. The biologist D.R.C. Thompson, in his seminal work on growth and form, argued that the shapes of living things are not arbitrary, but are physical solutions shaped by forces like tension and pressure, often resulting in forms of profound symmetry. We see this at the microscopic level, where the proteins that perform every task in our cells must fold into precise, symmetrical shapes to function. A single misfold, a break in that intricate symmetry, can lead to diseases. Even the branching patterns of a fern frond reveal a principle called self-similarity, where the same basic shape repeats itself at smaller and smaller scales, creating a complex whole from a simple, symmetrical rule. This fractal elegance appears in our own lungs and circulatory systems, maximizing surface area for efficiency. So when we see a butterfly's wings, we are not just looking at a pretty pattern. We are witnessing the same drive for order, the same principles of efficient structure, that shape galaxies and govern particles. Life itself appears to be a manifestation of these deeper symmetrical tendencies, a bridge between the abstract laws of physics and the vibrant, messy reality of biology. The mathematical language that gives voice to these cosmic patterns is known as group theory. At its heart, it is the study of transformations, the set of all actions you can perform on an object that leave it fundamentally unchanged. Think of a perfect hexagon. You can rotate it by 60 degrees or 120 degrees, and it still looks the same. You can also flip it over certain axes. Each of these actions is a symmetry operation, and the complete collection of them forms a symmetry group. This is not just about simple shapes. The deep, abstract symmetries that govern the fundamental forces are described by more complex structures called Lie groups, which are central to the standard model of particle physics. It is this precise mathematical framework that allows physicists to classify particles and predict their interactions with stunning accuracy. The profound connection between these abstract symmetries and the tangible laws of our universe was cemented by the work of mathematician Emmy Noether. In 1918, she published a theorem that would become a pillar of modern physics. She revealed that for every continuous symmetry in the laws of nature, there is a corresponding conservation law. The fact that the laws of physics do not change from one moment to the next, a symmetry in time, directly implies the conservation of energy. The fact that they are the same in every direction, a symmetry of rotation, gives us the conservation of angular momentum. Her insight was so powerful that Albert Einstein described her as the most significant creative mathematical genius thus far produced. To see this in action, look at a snowflake. Its intricate, six-fold symmetry is a physical manifestation of the underlying molecular structure of water, a pattern dictated by the crystal's symmetry group. The same mathematical principles that describe the rotations of that snowflake, a group known as SO3, also govern the quantum spin of an electron. This is the universal grammar of order, a language that translates seamlessly from the frozen beauty of a crystal to the frenetic dance of subatomic particles. As we learn to read this language, we equip ourselves to decipher the universe's most hidden and beautiful codes. This multiverse hypothesis presents a breathtaking vision of cosmic diversity. Within an infinite cosmic foam, each universe could be a unique experiment in symmetry, a bubble with its own distinct set of physical laws frozen into place during its birth. Our universe, with its specific gauge symmetries and broken electroweak force, is not the one true reality, but simply one that worked. One where the symmetrical conditions were just right for atoms, stars, and life to emerge. Elsewhere, the symmetries may have broken in radically different ways. Imagine a universe where the strong nuclear force is slightly weaker, preventing protons from ever forming. Another might have a different number of spatial dimensions, uncurled and expansive, where gravity fades too quickly for planets to coalesce. In such cosmos, the very concepts of chemistry or structure would be impossible, and no one would be there to wonder why. This cosmic landscape is not pure fantasy. Theories like eternal inflation suggest that the vacuum of space possesses a vast number of possible stable states, each with different energy levels and symmetrical properties. Our entire observable universe is just one bubble within an eternally inflating meta-universe, where new bubbles with different vacuum states are constantly budding off. String theory adds another layer to this picture with its own colossal landscape of possibilities. The specific way the extra Calabi-Yau dimensions are curled up determines the effective laws of physics in that universe, meaning there could be a staggering number of possible universes, each with a different symphony of symmetrical laws. Cosmologist Max Tegmark has categorized these ideas into levels of multiverses, from the simple realization that space extends far beyond our horizon to the more radical mathematical universe, where all structures that are mathematically possible exist physically. This brings us to a profound puzzle known as the measure problem. If there are an infinite number of universes, how do we calculate the probability of finding ourselves in one like ours? How do we measure what is typical in an infinite ensemble? It forces us to ask whether the hidden symmetries we have been exploring are fundamental truths, or merely the local bylaws of our particular cosmic neighborhood. They are the frozen accidents of our universe's specific cooling process. So when we marvel at the perfect balance that allows our existence, we are not looking at a universe fine-tuned for life, but life that has emerged in a universe capable of supporting it. The search for a single, ultimate symmetry holding our universe together transforms into a grander question. Are we simply inhabitants of one symmetrical possibility among a near infinity of others, each with its own unique and beautiful order? Deep beneath the border of Switzerland and France, the world's most powerful microscope hums with purpose. The Large Hadron Collider is not just a machine, it is a time machine, smashing protons together at nearly the speed of light to recreate the universe's first moments. Inside colossal detectors like ATLAS and CMS, billions of particle collisions occur every second, and each one is a potential window into a deeper layer of cosmic symmetry. For years, one of the primary targets has been supersymmetry, the elegant theory that posits a hidden twin for every known particle. Yet, despite this monumental effort, the detectors have remained silent. No squarks, no photinos, no sleptons have appeared in the data. This absence is not a failure, it is a message. As Fabiola Giannotti, CERN Director General, has emphasized, null results are not empty results. They are powerful constraints that force theorists to refine their beautiful ideas, pushing supersymmetry to higher energy scales or into more complex and nuanced forms. The dream of a simple, perfect sussy is fading, but the search for a more complex, hidden symmetry is more intense than ever. This iterative process is the very engine of science, a constant dialogue between imagination and evidence. The next phase of this quest is already underway with planned upgrades to the LHC and designs for future colliders. machines that will peer even deeper into the energy frontier. But the hunt for symmetry is not confined to particle colliders. Far away in deep underground laboratories, shielded from cosmic rays, other experiments lie in wait. They are searching for the gentle whisper of a dark matter particle bumping into an atomic nucleus. A single rare event in a vat of liquid xenon or a crystal of germanium could signal a collision with a WIMP or an action, revealing the symmetrical nature of the cosmos's hidden mass. We have even seen the fingerprints of subtle symmetry at work in the ghostly dance of neutrinos. These elusive particles change their identity as they travel, oscillating between electron, muon, and tau types. This metamorphosis is a direct manifestation of a broken symmetry in the neutrino sector, a delicate imbalance in their quantum states. Each of these experimental threads, from the violent collisions in a collider to the silent vigil of a dark matter detector, is part of the same grand tapestry. We are closing in on the fundamental patterns from all sides, testing the mathematical beauty of our theories against the unyielding reality of data. The universe's deepest secrets are not giving themselves up easily, but with every experiment, we are learning the rules of the hide-and-seek game it plays. The prevalence of symmetry forces us to confront a question that has haunted philosophers for millennia. Are the elegant mathematical patterns we discover the true, hidden architecture of reality? Or are they merely a beautiful story we tell ourselves, a lens our minds impose on a chaotic universe to make it comprehensible? This debate echoes the ancient divide between Plato and Kant. Plato believed our world is a shadow of a higher realm of perfect, eternal forms, ideal blueprints of which everything we see is an imperfect copy. The perfect circle drawn in geometry class is a glimpse of that ideal form. In this view, the symmetries of physics are not invented by us, they are discovered as we slowly uncover the divine geometry of the cosmos. Immanuel Kant, centuries later, offered a radically different perspective. He argued that our minds come pre-equipped with certain categories like space, time, and causality, through which we necessarily filter all our experiences. We cannot help but see the universe in terms of cause and effect, or in terms of symmetrical patterns, because that is the very structure of our perception. The symmetry is not out there in the thing in itself, but is a fundamental part of the glasses we wear to see anything at all. This philosophical tension is at the heart of modern physics. The physicist Eugene Wigner famously pondered the unreasonable effectiveness of mathematics in the natural sciences. Why should a system of logic and symbols, born from the human mind, correspond so perfectly and powerfully to the behavior of the physical world? It feels like a miracle, a gift we do not fully deserve. This uncanny alignment suggests that mathematics and the symmetries it describes might be tapping into something profoundly real. We see this power in action during the great paradigm shifts in science. The Copernican revolution was, at its core, a shift toward a more symmetrical model. Ptolemy's Earth-centered universe was a complex mess of epicycles and corrections, an asymmetrical patchwork to save the appearances. Copernicus offered a simpler, more harmonious system centered on the Sun, where planetary orbits became elegant, symmetrical circles. It was not perfectly accurate, but its aesthetic appeal and symmetrical elegance pointed the way to a deeper truth that Kepler and Newton would later reveal. This drive for beauty and symmetry is a powerful guide for scientists, often leading them to correct theories long before all the experimental evidence is in. Yet, we must also ask if our love of symmetry blinds us. Does the universe truly care about mathematical beauty, or are we simply pattern-seeking creatures, finding comforting order in the noise? The Anthropic Principle adds another layer to this puzzle. If we are here to observe the universe, then the universe must have the properties that allow for observers. The specific symmetries we find, from the strength of the nuclear force to the value of the cosmological constant, might not be necessary truths. but simply the local conditions of our particular cosmic neighborhood. In a vast multiverse of possibilities, we naturally find ourselves in one of the rare bubbles where the symmetries broke in a life-permitting way. So, are we uncovering the universe's secret code? Or are we just reading the bylaws of our own habitable zone? This is not merely an academic debate. It strikes at the heart of what it means to know something. Is symmetry a fundamental feature of reality, waiting to be discovered? Or is it the most powerful lens our human minds have yet devised to make sense of a reality that is ultimately beyond our full comprehension? The answer may lie somewhere in between, in the silent dialogue between a rational cosmos and the conscious minds that have emerged to admire its hidden order. Look up at a spiral galaxy like the Whirlpool Galaxy, and you are witnessing symmetry on a scale so vast it defies human comprehension. Its majestic arms sweep out from a brilliant core in a near-perfect spiral, a frozen whirlpool of stars and gas. This is not a static sculpture, but a dynamic structure held in balance by gravity and dark matter. The entire galaxy rotates, and that rotation should, by the simple laws of motion, cause the outer arms to wind up tightly over billions of years, destroying the spiral. Yet the pattern persists. The symmetry endures because it is not a rigid shape, but a density wave, a gravitational pattern that moves through the galactic disk like a ripple on a pond. Stars and gas flow into this wave, compressing to form the bright arms before flowing out again. This grand design is a direct manifestation of the symmetrical pull from an invisible halo of dark matter, a hidden scaffold that governs the galactic dance. Edwin Hubble, who first classified these island universes, saw in their forms a cosmic order. He described the elegant sequence from featureless ellipticals to majestic spirals, a taxonomy based on their symmetrical properties. But perfect symmetry is a theoretical ideal. The real cosmos is shaped by violence and interaction. When galaxies drift too close, their mutual gravity stretches them, creating tidal tails of stars flung into the abyss. These collisions and mergers are the great sculptors of the cosmic zoo, breaking simple symmetries to create the rich diversity of forms we see in Hubble's deep field images. Peculiar galaxies, ring galaxies, and majestic antennae galaxies are all testaments to this creative destruction. On the very largest scales, the universe reveals its most profound symmetry of all, the cosmological principle. This is the idea that, when viewed on a scale of hundreds of millions of light years, the universe is both isotropic and homogeneous. It looks the same in every direction, and matter is evenly distributed. This large-scale symmetry is the ultimate legacy of cosmic inflation, that moment of ultra-rapid expansion that stretched the primordial universe to incredible smoothness. The cosmic microwave background, the afterglow of the Big Bang, is the ultimate proof, a snapshot of a newborn cosmos that is almost perfectly uniform, with temperature variations of only 1 part in 100,000. From that symmetrical seed, gravity worked over billions of years to weave the cosmic web we see today. A vast network of galaxy clusters and filaments surrounding immense voids. This web is not perfectly regular, but it possesses a statistical symmetry, a predictable pattern in the clustering of matter that mirrors the tiny quantum fluctuations imprinted at the dawn of time. So when you gaze at an image of a galaxy, you are not just looking at a collection of stars. You are seeing the final expression of a symmetry written into the fabric of the cosmos at its birth, a pattern shaped by dark forces and gravitational poetry, a single note in a symphony of structure that stretches across the entirety of observable space. The search for symmetry is accelerating, powered by machines that think in quantum probabilities and telescopes that see with infrared eyes. Quantum computers, with their qubits existing in superpositions, are uniquely suited to simulate the very quantum fields and complex symmetry groups that underpin reality. They can model the behavior of a system like the Higgs field in its earliest, most symmetrical state, offering a digital window into cosmic phase transitions that are otherwise lost to time. Meanwhile, in the silence of space, the James Webb Space Telescope peers back to the dawn of the first galaxies, its observations testing the large-scale symmetrical predictions of the cosmological principle to their limits. Any subtle anomaly in the distribution of these ancient structures could hint at a primordial symmetry we have not yet imagined. Theoretical physicist Lisa Randall suggests that the next breakthrough may not come from a single instrument, but from a confluence of data, where gravitational wave observatories detect ripples from the early universe's most violent symmetry-breaking events, while AI algorithms sift through the noise to identify novel mathematical patterns and symmetry groups hidden in the data. This is not science fiction. We are already seeing glimpses of this future in laboratories here on Earth, in the study of exotic materials known as topological insulators. These crystals possess a hidden symmetry in their electronic structure that forces electrons to flow without resistance along their surfaces, a property that could revolutionize electronics. This is an emergent symmetry, a collective behavior of billions of atoms that gives rise to a new, stable state of matter with profound practical applications. It demonstrates that discovering a new symmetry is not just an abstract triumph. It can literally power the next generation of technology. The ultimate goal remains a theory of quantum gravity, and many believe the path leads through a deeper understanding of symmetry. Projects like the proposed Future Circular Collider would push our probes to even higher energies, directly exploring the terrain where gravity and the other forces might finally reveal their unified, symmetrical origin. We stand at the threshold of a new era, where our tools are becoming sophisticated enough to read the universe's most fundamental code. The hidden order that has whispered to us since the time of the ancient Greeks is now within our reach, waiting to spark a scientific revolution that will redefine our place in the cosmos. Every bit of information in the universe is a whisper of order against the roar of chaos. This is the domain of information theory, a field that reveals a stunning connection between symmetry and the very nature of data. Claude Shannon, the father of this science, understood that communication relies on patterns and predictability, which are forms of symmetry. When a message contains a repeated, symmetrical structure, it can be compressed into a simpler code, transmitted efficiently, and then perfectly reconstructed on the other side. The universe itself appears to operate on this principle, using symmetrical laws as a form of cosmic data compression, reducing the infinite complexity of reality into elegant, repeatable equations. This deep link becomes even more profound when we consider the physical cost of information. Landauer's principle states that erasing a single bit of information inevitably increases the entropy of the universe, releasing a tiny amount of heat. This means information is not an abstract concept. It has a tangible, energetic footprint. The act of forgetting, of resetting a cosmic memory register, literally fuels the arrow of time. Now, consider how symmetry protects this fragile data. In quantum computing, scientists use symmetrical arrangements of qubits to build error-correcting codes. These codes are designed so that if one qubit flips, the overall symmetrical pattern is broken, and the error can be detected and fixed without even looking at the individual qubit's state. This is symmetry in action, serving as a guardian of quantum information against the relentless decay of decoherence. This protective role of symmetry is pushed to its absolute limit in the most extreme environments we know, black holes. The no-hiding theorem is a powerful result in quantum mechanics that states if information disappears from one part of a system, it must reappear somewhere else. It cannot be simply erased. This theorem relies on the symmetrical, unitary evolution of quantum states. In the context of a black hole, it suggests that the information about what fell in is not lost inside the singularity, but is somehow encoded on the event horizon, preserved in a scrambled, symmetrical form. This is a crucial piece of the puzzle in resolving the black hole information paradox, pointing toward a universe where symmetry enforces a strict cosmic accounting system, ensuring no data is ever truly destroyed. We see this same principle of efficient, symmetrical encoding in the very blueprint of life. The DNA in every one of your cells is a masterpiece of information storage. Its double helix structure possesses a beautiful symmetry, with each strand mirroring the other. This symmetry is not just for show. It is a functional redundancy that allows for reliable replication and robust error correction. The genetic code itself uses symmetrical patterns to minimize mistakes when proteins are assembled, ensuring that life can transmit its essential information across generations with incredible fidelity. From the spin of an electron to the spiral of a galaxy, symmetry emerges as the universe's fundamental tool for managing information. It compresses the laws of physics, corrects errors in quantum data, and preserves the story of what falls into a black hole. This suggests a breathtaking possibility, that the cosmos we perceive may be the most efficient possible expression of a deeper, informational reality. The order we marvel at, and the data that defines existence are not separate things, but two sides of the same symmetrical coin. Our own creations echo this cosmic obsession with balance. Long before physicists wrote equations, architects were building symmetry into stone. A Gothic cathedral rises with perfect bilateral symmetry, its twin spires and stained glass windows mirroring each other, drawing the eye and the soul upward. This is not merely an aesthetic choice. It is an architectural prayer, a physical manifestation of a belief in a higher, divine order. The same impulse guides the intricate geometric patterns adorning Islamic mosques, where infinite, repeating tessellations symbolize the unending and omnipresent nature of creation. These artists were not just decorating. They were encoding a worldview, using mathematical precision to reflect a universe governed by harmonious, unbreakable laws. This drive for balance resonates in sound as well. The symphonies of composers like Beethoven are built on symmetrical structures, with themes stated, developed, and then resolved, creating a profound sense of completion and emotional satisfaction. We feel this harmony in our bones. It is the rhythm of a heartbeat, the balanced repetition of a chorus, the universal grammar of order translated into music. Why does a symmetrical face seem more beautiful to us, or a balanced composition in a painting feel more serene? Cognitive scientists suggest our brains are hardwired to find pleasure in symmetry. It signifies health, predictability, and efficiency. It is easier for our minds to process, a signal that all is well, that order prevails over chaos. This innate preference points to something deeper than culture. It hints that our aesthetic sense is tuned to the fundamental frequencies of the cosmos itself. Leonardo da Vinci's Vitruvian Man perfectly captures this fusion of art and cosmic principle. The figure, with his outstretched limbs touching both a circle and a square, embodies the ideal human proportions that Leonardo believed were a microcosm of the universal order. He was searching for the canonical, the perfect ratios that he saw reflected in nature, from the branching of trees to the spirals of shells. This quest leads us to the golden ratio, often denoted by the Greek letter phi. This irrational number, approximately 1.618, appears with uncanny frequency. You can find it in the arrangement of a sunflower's seeds, the spiral of a nautilus shell, and the proportions of the Parthenon. It is a specific, asymmetrical symmetry that the human eye finds exceptionally pleasing. While its prevalence is sometimes debated, its power as an ideal is undeniable. It represents a universal standard of beauty, a hidden mathematical thread connecting art, nature, and the human form. From the mandalas of Eastern spiritual traditions, used as tools for meditation to represent the universe and the self, to the rhythmic patterns in tribal dances, humanity has consistently reached for symmetry to make sense of the world. This is not a coincidence. It is a profound clue. Our artistic and cultural expressions of balance are not separate from the physicist's search for gauge symmetry or the cosmologist's model of inflation. They are different dialects of the same fundamental language. We are not just studying the universe from the outside. We are expressions of its deepest principles, and our most enduring art is a conscious celebration of that hidden, beautiful order. A snowflake drifts down from a winter sky, its six-fold pattern a tiny miracle of natural engineering. This intricate design is not a rare exception, but a constant presence in our world. The principle of symmetry provides the silent, underlying stability for countless aspects of our daily lives. Consider the simple act of riding a bicycle. The wheel is a masterpiece of radial symmetry, with its spokes radiating from a central hub. This perfect balance distributes stress evenly, allowing for smooth, efficient motion. Without this symmetry, every rotation would be a wobbly, jarring struggle. Nature itself is a master architect of efficient form. Look at a honeycomb, its walls forming a perfect hexagonal grid. This pattern is not an aesthetic whim. It is the solution to a profound engineering problem. The hexagon allows bees to create the largest possible storage space for their honey using the smallest amount of precious wax, achieving maximum strength with minimal material. This same drive for efficiency and stability, guided by symmetry, shapes our own creations. The Eiffel Tower stands as a monument to this principle. Its iconic lattice structure is not just beautiful, it is brilliantly engineered. The symmetrical arrangement of its iron beams creates a framework that is both incredibly strong and remarkably lightweight, able to withstand powerful winds by distributing forces evenly throughout its form. Even our own bodies are testaments to bilateral symmetry. Your left and right halves are nearly mirror images, a body plan shared by most animals. This arrangement is no evolutionary accident. It allows for balanced, streamlined movement, whether you are running, swimming, or simply walking across a room. It gives us a clear forward direction and helps coordinate complex motions. Why does a symmetrical face so often strike us as beautiful? Cognitive science suggests our brains are wired to associate symmetry with health, genetic fitness, and efficient function. It is a subconscious signal that all is well. Take a moment to look around you. The city you live in is likely laid out on a grid, a symmetrical pattern that organizes space and simplifies navigation. The device you are using to listen to this was designed with symmetrical components for optimal performance and aesthetic appeal. The very chair you are sitting in relies on balanced forces to support your weight. These are not abstract concepts from a physics textbook. They are the tangible expressions of the same cosmic principles that hold galaxies together. The hidden order of the universe is not confined to distant stars or quantum fields. It is woven into the fabric of our everyday reality, providing a foundation of stability, efficiency, and quiet beauty that makes our complex world possible. Yet for all the elegance of this symmetrical framework, profound cracks are appearing in our understanding. The universe presents us with puzzles so deep, they challenge the very foundations of our theories. One of the most stubborn is the hierarchy problem, a question of cosmic proportions. The mass of the Higgs boson is incredibly small compared to the enormous Planck scale, the energy at which gravity becomes strong. According to our current equations, quantum fluctuations should have driven the Higgs mass to a value 1 trillion times larger, making our universe impossible. Why is the weak force so much stronger than gravity? This vast disparity seems unnatural, a fine-tuning that begs for an explanation like supersymmetry, yet the predicted particles that would solve it remain frustratingly out of reach. Another gaping mystery is the nature of dark energy. The cosmological constant, the simplest explanation for the accelerating expansion of the cosmos, has a value that is not just small, but absurdly so. Theoretical predictions overshoot the observed value by a staggering 120 orders of magnitude. This is the worst prediction in the entire history of physics, a glaring sign that we are missing something fundamental about the vacuum of space itself. The physicist Steven Weinberg once reflected on this fine-tuning, suggesting that the constants of nature appear to be balanced on a knife's edge, a coincidence that cries out for a deeper explanation. Then there is the strong CP problem, a mystery so subtle it involves the nuclear force. The strong interaction which binds quarks together appears to perfectly respect the combined symmetries of charge and parity. This is strange because nothing in our theories forbids it from violating this symmetry, just as the weak force does. Its perfect obedience feels like a cosmic oversight, as if a dial that could have been turned has been mysteriously set to zero. Why is the strong force so impeccably symmetrical in this one specific way? Proposed solutions like the hypothetical action particle only deepen the mystery, offering a new candidate for dark matter while highlighting our ignorance. We are also confronted by the enigmatic origins of neutrino masses. These ghostly particles have mass but vanishingly little, and we do not fully understand the mechanism that gives it to them. Their behavior hints at new symmetries or new types of particles operating at tremendously high energies, far beyond our current reach. These are not isolated issues. They are threads in a larger tapestry of theoretical tension, most notably the glaring conflict between the symmetrical world of quantum mechanics and the geometric elegance of general relativity. We have two magnificent, powerfully accurate theories that describe reality, yet they speak different languages and refuse to be united. This is the greatest unsolved problem in fundamental physics. Every attempt to quantize gravity or to find a symmetrical framework that encompasses both leads to new questions, or to mathematical infinities that our current tools cannot resolve. These challenges are not signs of failure. They are the frontiers of discovery, the cosmic puzzle pieces that do not yet fit, driving scientists to build more powerful colliders and more sensitive telescopes. The journey to understand the hidden symmetry of the universe is far from over. It is an ongoing quest, fueled by the conviction that for every beautiful mystery we solve, an even more profound one awaits just beyond our sight. From the cosmic balance of ancient Greece to the holographic projections of modern physics, our journey reveals a universe woven together by hidden symmetries. These are not abstract decorations, but the fundamental principles that dictate why energy is conserved, how particles acquire mass, and what forces bind the atoms in our bodies. They are the silent rules behind the predictable swing of a pendulum and the spontaneous breaking that gave our universe its substance through the Higgs field. This elegant order points toward a grand unification, a dream that all of nature's forces were once one, a single, symmetrical expression of reality in its first, fiery moments. This quest for cosmic order resonates far beyond the equations of physics. It is the same drive that compels an architect to design a symmetrical cathedral, or a composer to structure a symphony around a recurring theme. Our technology, from the perfectly balanced wheel to the error-correcting codes in quantum computers, borrows directly from nature's playbook of stable, efficient design. We are drawn to symmetry because we are products of a symmetrical universe, and our deepest art and most ingenious inventions are conscious celebrations of that hidden order. Albert Einstein once marveled that the most incomprehensible thing about the universe is that it is comprehensible. It is this very comprehensibility that symmetry provides, a logical framework that allows our minds to grasp the cosmos. The fact that we can uncover these patterns, that we can write down laws that hold true across billions of light years, is a testament to a deep, rational order underlying everything. Perhaps this is the most profound symmetry of all, the mirror between the human mind and the mathematical structure of reality. I would love to hear your thoughts on these ideas in the comments below. What aspect of cosmic symmetry fills you with the most wonder? If you enjoyed this deep dive into the mysteries of space, please subscribe for more journeys to the edge of our understanding. Let this exploration be a starting point, a spark to keep looking at the world around you with fresh eyes, to see the elegant design in a snowflake, a spiral galaxy, and the very fact of your own existence, all held together by the universe's beautiful,